All right, in this video, I'm going to look at reaction profile graphs, or simply reaction profiles. I'm going to skip over talking about collision theory and the different factors that affect reaction rates because there's two great videos on the Kinetics page of my website under multimedia that will talk about the factors that affect reaction rates as well as what collision theory is. So if you need help on those two subjects, check out those videos on my website. So for our reaction profile, what a reaction profile is simply a graph that's going to show us what the energy changes in our reaction are going to be. So if we did a reaction profile for an exothermic reaction, so our exothermic reaction is going to release heat. So this is for an exothermic reaction with a negative delta H. And remember that negative just means that it's an exothermic reaction. It doesn't mean we end up with negative amounts of energy, it just means we're releasing energy rather than absorbing it. So to do a reaction profile for an exothermic reaction, we're going to release heat, which means the resulting heat of my products is going to be less than the initial heat of my reactant. So it's going to look something like this. Okay, so this is going to be my reactants, and this is going to be my products. As you notice, the energy of my reactants is higher than the energy of my products. So to get from my reactants to my products, I would need to release heat. Okay, so now let's kind of break down this graph and see what else it's going to tell us. So if I draw a little dashed line from my reactants, from the plateau of my reactants and the plateau of my products, I'm going to get this section right here. This section is my delta H. My delta H is equal to the heat of my reaction, or how much energy in this case is being released. So I can put a numeric value and I can say that, let's say this is equal to 100 kilojoules. So what this is saying is that this reaction, my forward reaction, going in this direction, going from left to right, from reactants to products, is going to release 100 kilojoules of energy. Okay. Next, I have this section right here. And what this point is called, this peak, is actually called my activated complex. And this is the point at which my molecules in my reaction, or most of my molecules in my reaction, have enough energy for successful collisions to occur, so for my reaction to occur. So this red arrow between the energy of my reactants and my activated complex is called my activation energy, okay, or EA for short. So activation energy. And my activation energy is just the energy needed to get my reactants to the proper or required energy for the reaction to happen. Okay? Sorry, I forgot one thing on my graph. I should label my x-axis is actually time, and my y-axis is energy. Okay, so for my forward reaction going from reactants to products, I'm going to release 100 kilojoules of energy, and I have my activation energy is indicated by the pink arrow, and I can put a value on that too. I'll say my activation energy, I required 20 kilojoules of energy. So now, if my forward reaction was exothermic, this means that my reverse reaction is going to be endothermic. So I can make this a little bit smaller, and I'm actually going to write or draw the reverse reaction of this same reaction. So I'm just going to draw the reverse reaction of my initial reaction profile. So this is going to be my endothermic reaction with a positive delta H. So my reverse, my endothermic reaction is going to look like this as I absorb heat. So again, this is going to be my time, and this is going to be my y-axis. It's going to be energy. Okay, and I can fill everything in the same way that I had on my other graph, except in this case, my products have now become my reactants, and my reactants have become my products. Okay, so this reaction moving in this direction is the same as this reaction moving in this direction. Okay, so if I fill in my value, so my delta H is still going to be 100 kilojoules. But if a question asked me what is the delta H for this reaction, for my forward reaction in this graph, my delta H would be 100 kilojoules. If it asked me for the delta H of the forward reaction in this graph, my delta H would be negative 100 kilojoules, with the negative denoting that it's an exothermic reaction. Now, instead of my activation energy being here, my activation energy is still the energy required to go from my reactants to my activated complex. So my activation energy for my reverse reaction, or for my endothermic reaction, is going to be this part right here. So let's say let's keep my activation energy. So in green, actually I can make this green too to make them match. So my green is my activation energy for my forward reaction. And we already gave that a value. We said that was 20 kilojoules. So if I want to find my activation energy for my reverse reaction, or for my endothermic reaction, all I have to do is, so my activation energy for this reaction is going to be equal to my delta H plus the activation energy of my forward reaction. So it's going to be 100 kilojoules plus 20 kilojoules. So my activation energy for my endothermic reaction is 120 kilojoules. So no matter what they give us, if they give us two of the three pieces, either our activation energy for our reverse reaction or for our forward reaction and our delta H, we can find the other piece. So there's a relationship between our activation energy of our forward, our activation energy of our reverse, and our delta H. And if I have two of those three pieces, I can find the third piece. So if I'm given the activation energy of the forward and the delta H, I can find the activation energy of the reverse. Or if I'm given the activation energy of the reverse and the delta H, I can find the activation energy of the forward. Notice that our delta H did not change. Our delta H is going to have the same value for both our endothermic and our exothermic, for both our forward and our reverse reactions. The only thing that's going to be different is the sign, if it asks you what the delta H is for a particular reaction. So it's only going to be the sign that's going to be different. The numerical value is going to be the same. All right, let's make this all a little bit smaller. And there's one other thing I want to show you with these reaction profiles. So if I have a reaction profile, let's go back to an exothermic reaction. So here's my exothermic reaction. And as we said, so this for my forward reaction, this is my activation energy. And remember, the activation energy is the energy required to go from the energy of my reactants up to the required energy for my activated complex. So one way in which to speed up a reaction is to add a catalyst. So if I add a catalyst to this, what I'm actually going to do is change the reaction pathway by lowering the activation energy. So notice when I lower the activation energy, the only thing that changes is the activation energy. So my activation energy is now this portion right here. Notice my delta H right here did not change. It doesn't matter what my activation energy is. My delta H is going to remain the same because the initial energy of my reactants and the final energy of my products is going to remain the same. When I add a catalyst, it's going to alter the reaction pathway by decreasing the activation energy. So it's going to take less energy to go from the energy of my reactants to my activated complex. Okay, so if you're asked to draw a reaction profile, this is how you would do it, and those are all the pieces that go into a reaction profile.